broke up this page for you guys, but last semester I did a little differently, so I have something full of it. You don't have to worry about that. Alright, this one right here, it's approximately normal because of the central limit theorem. You would find your mean standard deviation. You want to just find the probability that the mean for a sample is greater than 2. So you get, I think it's 8 to the negative 10 to the negative 4th. So there's a 0.08% chance a sample of 28 cars have a mean number of passengers greater than 2 people. Good? Alright, so I'm gonna have you guys look at, somebody came in this morning and asked me a question about that finite population connection. And so I thought there was a problem in the book I thought would be good to look at. It's not one of the ones that I had assigned, so we're gonna look at this one problem here. See if it'll help you get a little bit of a better understanding of what's happening here. So I'm gonna have you guys, you could just do it at the bottom of this page if you wanted. We're gonna do number 26 here. Unfortunately, it's pretty big. So for me to, if you wanna pull up the online book and look at it that way, but this is number 26 in section 5D. It's page 516. So I want you to just to attempt this problem right now. Again, it's 26 on page 516 if you can't see it very well. So you can just use the space below to attempt it.
Standard, can you get water real quick?
Yep. Alright. Alright, what I wanted you to get from this question is the importance of that 10% check. So, if the 10% condition was not met, this is the correction that you have to do. Again, you will never be asked to do that correction in this course, but you should just be aware that this is why the 10% is so important. So if you, for the first one, we were meeting the 10% condition. So they were saying, okay, here's the formula without the correction, you get 1.58. Here's the formula with the correction, so then you get 1.57, so it's not that different. So since the 10%'s been met, that's why we just go ahead with the basic formula, okay? But then once the 10%'s not met, you can start to see that we end up with very different numbers. And it tries to, I'm gonna come back to this idea in 1 second here. And C, it asks you, based on the answers, explains why we can use the formula when we are less than 10%. Again, the reason why we're using the formula when we're less than 10% is because the answers are practically the same, okay? In part D, it said you were taking the entire population as your sample size. So when you plug everything into the correction, you end up with a standard deviation of 0. That should make sense. There is only one sample of 1,000. So if I take, there's only one combination. If I have a population of 1,000, there's only one sample of 1,000. So if I take the mean of that, it has to be the population mean, so there has to be no variation. There's only one value, okay? Again, so 1,000 is not less than 10% of the population. So that is why we have to use the correction. If I didn't use the correction, I'd get 1.58. That can't make any sense, alright? So what the reality of it, if you take a sample that is bigger than 10% of your population, that formula right there, and this is the same thing's true for the proportion. This formula isn't decreasing at a rate fast enough to capture how fast the standard deviation is actually decreasing. So that's why we have a correction. This correction makes that number smaller because it's decreasing faster than the original formula is accounting for, okay? And again, the correction is actually the same if we were talking about the standard deviation of p hat, okay? All right. Again, the only thing that you really need to take away is that 10% condition has to be met in order for us to use this formula, or this formula. If that 10% wasn't met, this formula isn't capturing how quickly the standard deviation is decreasing, and that's why there's a correction done, okay? Again, you're not going to be asked to do the correction or anything like that. You just have to be able to use that 10%. All right. Any questions on anything before we start today's lesson? All right. I'm going to start off. So today I just decided to lump both of the two sample stuff together as opposed to doing it separately or trying to squeeze it in when I did the one sample stuff. So I'm going to start off with p hat 1 minus p hat 2, and then we'll talk about what x bar 1 minus x bar 2 means. This is a lot of our procedures later on that we'll deal with. We'll deal with two sample stuff. Like if you wanted to compare underclassmen versus upperclassmen, you're talking about two samples there, okay? So the question here is it harder to shoot free throws with distractions? To investigate, a basketball player went to the gym and shot 20 free throws. 10 of the free throws were shot without any distractions, and the other 10 were shot with his friends trying everything they could to distract him. The order of the 20 shots was determined at random. So that means like they randomly decided, he was about to make a shot, and they randomly decided were they going to distract him or not. All right, go ahead and answer number 1. All right, why was it important that the order of the shots are determined at random? Hold on.
To eliminate bias?
To eliminate bias, I would say to probably eliminate or try to reduce confounding variables. What might happen if we had him shoot all the first shots were without distractions and the second shot were with distractions? And let's say he's worse with the distractions. Is it because of the distractions? Or is it just because he got tired? So you wouldn't necessarily know. So I want to randomly assign the shots to reduce the impact of confounding variables. As an example, if he gets worse because he's tired, so if he did all the distraction shots last, we wouldn't be able to determine, was it because the distractions were causing him to be worse, or is it because he was just tired because he kept doing it, okay? Or vice versa, maybe he got better, okay? Everybody clear there? All right, down here, he makes 5 of the shots in the distraction-free environment and 3 of the shots in the distraction environment. Remember, there was 10 of each. Let p hat 1 be the sample proportion shots made in the distraction-free environment. And then let p hat 2 be the proportion of shots made in the environment with distractions. So calculate P1, P hat 1, and P hat 2. So there's two proportions here. All right, what's P hat 1, Madeline? You don't know? Elena?
Is it 0.5?
Yeah, it's just 5/10, 0.5. 5 out of 10. And then Ellie, what's P hat 2?
3 out of 10.
Yeah, 3 out of 10. Okay, so 0.5, 0.3. Everybody understand? All right, part 3, it says calculate the difference. Notice I had P hat 1 minus P hat 2. So I have no so the distraction free minus the distractions. So what's the difference, Kyle? Yeah, 0.2. All right, the difference is positive. All right, so difference is positive. That means the distraction free is higher. All right, I've asked this kind of question before. So there's two explanations for why it looks like it's positive, why the distraction free is higher. What's one of the explanations for why the distraction free is higher?
It actually impacted the outcomes.
It actually what?
Impacted the outcomes.
Yeah, isn't that what you're, okay. So it actually is easier to shoot. To shoot without distractions. So there is like the distractions are actually causing the reduction. The other explanation is what? It just happened due to chance. The difference is due to chance. All right, so that's what we need to figure out. That's always what we're trying to figure out. We're trying to figure out is something actually impacting those results or is it just due to chance? So we're going to simulate this. We're going to simulate what could happen, and then we'll look at what did happen to see if it was chance or if something was actually causing that difference. All right, so first thing we're going to do, remember, I made this little table down here for you. We have makes the shot. So I'm going to say that's a successful, like a bucket. The environment, either the free of the distractions or distractions. Remember, he made yes. So in the yes, in the in the environment free of distraction, he makes 5 of the shots. So that means he misses how many? 5. In the distraction free environment, he makes 3 of the shots, so he misses 7. So in total, he makes 8 shots out of the 20. He misses 12 shots out of the 20. So regardless of the type of shot, what's his proportion? This is actually P hat C, but we'll worry about that notation later. What's the success rate? Ignoring the environment that he's in, what's his success rate? 0.4, so it's 8 out of 20. 0.42 fifths. All right, that's his success rate ignoring the environment that he's in. Yes? All right, so what we're going to do with this simulation here is we're going to kind of pay attention to what happens in total. So we're going to say this is his overall success rate, that 8 out of 20. So we're going to assume P1 is the proportion of shots made in the distraction free. And we're going to assume that it's equal to P2. So we're going to assume it doesn't matter which environment he is. He always has a 40% success rate. Okay? First thing I want you to do, I gave you some cards. Grab those cards. Should be enough for everybody to have their own. I'm flipping the page here. Again, you got it. Well, you can flip the page, but I'm flipping back for a second. Just look up here. You should have 8 yeses and 12 nos. So double check that for me first. Anybody not have 8 yeses? At some point in my life, somebody stole a yes from me, so one of my decks is missing a yes. But does everybody have 8 yeses and 12 nos? Alright, I'm not hearing anybody, so it looks like we're all good. Alright, remember, he has a 40% success rate. That's what you have right here in all these cards. So, what I'm gonna do here is I'm gonna take my cards and we wanna kinda shuffle them, like mix them up. Cause this is what would happen by chance. So by chance, that we would just randomly, it would just, these would fall out however they fell out, if it was just by chance. So I'm shuffling them all up. And then I'm going to create two piles here. So the first pile is going to be free of distractions. Distractions, free. And I'm just gonna separate the cards into 2 piles. And I should have 2 piles of 10. And my first environment was without distractions, so free of distractions. My second environment is with the distractions. I've got 3 yeses here, 5 yeses here. If I do the subtraction, I'd have -2 tenths, so I have -0.2 in my first trial. So you can get negative by chance. Everybody clear on what's happening? You're gonna repeat that 4 more times, and then we're gonna put all of our trials together. Once you have your numbers, you're gonna go to this web page to load them up for me. I'll wait. Make sure you keep that subtraction order the same. And it's okay to be negative, that just means you have more shots in the distraction environment. Remember, we're trying to see what happens by chance. order for everybody, or you can all go in there on your own, it doesn't matter. I want everybody's numbers in here. You're gonna go to this Staplet.com. When you get to that main screen, there'll be a list of choices. You wanna look for the one that says one quantitative variable single group, and you wanna click on that word collaborative. And then the class code is up there. And again, if you want one person at your table to type them in for everybody, you can do that. Or you can all do it individually if you don't like people at your table.
I wanna type mine in.
Yeah, that's why I thought.
Oh, yeah, true.
Cause you only have 8 guesses, so you could only get certain combinations.
Maybe,
So you just type them in right there,
Just
put the number in like points,
like
Yep.
8.2.
yep, point 2, then comma, point 2. So like, yep, or do it one at a time like that. Yep.
You can do comments.
Oh, you have to do it one at a time?
Yeah, I can.
Okay, just one at a time then.
Where do you enter in the number?
So you go to the one that says collaborative.
Yeah.
Okay, then you, okay, hold on, let me, I'll just need to extend the data collection. So it should work now. Does it allow you now? You might have to refresh it.
Yeah.
Yeah.
And then just enter each.
Yeah, I guess you have to enter them in one at a time. Your eyelashes are already very dark, so I don't, like, they're, so, but I mean, I wouldn't, like, know if you didn't though either, like. There's 22 of you here. No, there's 20 of you here today. No, there's 22 of you here. So I should have 110 dots. Isn't it, this is I guess so. But I still don't think physics formulas are beautiful. I feel like I'm missing 3 data points, but we'll let it go. Somebody probably just thought they typed them in and did it. I got everybody's orange cards, right? Somebody has to be like difficult. Who's the prankster? They wanted to, yes. I have to figure out how. They have to undo it though, I think. Oh, actually, no, I can do it. Schmuck. I'm gonna get rid of that prankster now. I paused the data collection. Alright, if you look here, so again, the dot plot represents what can happen by chance. You literally were shuffling those cards just randomly and you gave me this. And like I said, this is really beautiful. Like it couldn't have worked out better. Alright, so then what do we want to figure out? What happened in real life is that we saw a difference of 0.2. So I want to find the probability of it being 0.2 or higher. So it counts the dots for me. There's 36 dots there out of, we have 107. So I have a 33.6% chance here. So it's about a 33% chance of observing 0.2 or higher. I'm going to flip back to our other screen. So it's 33.6 in our simulation. I'm still 33. It was, how many was it? It was 36 dots out of 107. I'm going to come back over here. I'm trying to record this for everybody at home. Okay. So we had 36 dots out of 107. What did I say? It was 33.6%. All right, down here, I did the same thing. I used technology, and I simulated it 10,000 times using technology. All right, here, this right here actually is 32.85%. So we're always, it looks like we're about at a 33% chance of observing a difference of 0.2 or higher, just by chance alone. Okay. So, answer number 8 right now. Talk to your table. Correct. So is there convincing evidence he's better? Yes or no? Alright, this one, yes, there is convincing evidence. Alright, again, think about what this means. So if there is a, we'll say about a 33% chance of observing a difference of 0.2 or higher by chance alone. So there is not convincing evidence he is better without distractions. Do you understand what we're saying? Because it's so likely to observe that by chance alone. So since it did happen, that's not any evidence that he actually got arrested. Correct. What if he made 8 shots in the distraction-free environment and made 0 shots in the environment with, so 8 shots in the distraction, 0 shots with 8 shots without distractions, 0 shots with distractions. So the difference would have been 0.8. Would that have been evidence?
Yes.
Yes, because that is unlikely to happen by chance.
It could.
It could still happen. But that's everything in life,
That's true.
right?
That's why it's
Everything
supposed to
could
be
still happen, but if it's unlikely to happen, that's when you have to be suspicious, okay?
It's like, what would you say if it was 7? Like, how do you know where the space
So
is?
that's,
As my sister.
later on, the book will tell you use 5% as your threshold.
I can't do the eyebrows.
So you want it to be like 10% probably isn't that unusual, 5% starts to get unusual, okay? Alright, so I tried to give you an idea with that activity, what that sampling distribution of p hat 1 minus p hat 2 would look like. So again, you think about all possible combinations of p hat 1 minus p hat 2. The mean and standard deviation. So the mean is actually, in this case the mean was 0 because I was assuming the two proportions were equal, so the difference was just 0. That's not always the case. That's often the case what we'll assume in this class, but the mean, the difference in the two proportions is actually the difference in the two p's. The standard deviation is also kind of using the original standard deviation from the other day. The formulas are on the formula sheet. I'm going to derive them for you below. So the mean of p hat 1 minus p hat 2 is just the difference in the two proportions. The standard deviation of p hat 1 minus p hat 2 looks similar to this formula. You notice you have some 1s and 2s in there. Again, the formulas are on the formula sheet. You don't have to memorize them. I'm going to go through where they come from down here. All right. Again, not chapter 6. I gotta fix this. Unit 4, part 2. The formulas are from Unit 4, part 2. All right. So it says, let's find p hat 1 minus p hat 2. Okay. If I go back to Unit 4, part 2, we said the mean of x minus y was equal to the mean of x minus the mean of y. So here, this is like saying the mean of p hat 1 minus the mean of p hat 2. The mean of p hat 1 has to be equal to what? Just think about the other day. The mean of p hat is equal to p, so the mean of p hat 1 is equal to p1. And then the mean of p hat 2 is equal to p2. Alright, so the mean of the difference is just equal to p1 minus p2. Again, that means that it is an unbiased estimator. So p hat 1 minus p hat 2 is an unbiased estimator because the mean of all the p hat 1s minus p hat 2 is equal to p1 minus p2. Alright, where's the standard deviation formula coming from? Again, remember, to find the standard deviation of the differences, we add the variances. So, the variance, well actually let's do this. Let me write it like this. That's a little less confusing if I start there first. Alright, so I'd have to add the variance of the first one plus the variance of the next one. Alright, the standard deviation of p hat. I'm gonna make it look really ugly and then I'm gonna erase something. The standard deviation of p hat would be p minus times 1 minus p over n. I'm gonna put 1s here. So I'm gonna say p1, 1 minus p1 all over n1. That's the standard deviation, but I want the variance. So what am I doing with that quantity? I'm squaring it, so that essentially means I'm getting rid of that square root. Does that make sense? And then the same thing over here would happen. I would have a square root that I would square, but there'd be all twos here, so that's where that formula is coming from. This is only true if N1 is less than 1/10 of population 1 and N2 is less than 1/10 of population 2. Otherwise, there's a more complicated correction that has to be done. Oh, and I didn't answer this question up here. The sampling distribution of when will it be approximately normal? So you saw right here that it looked approximately normal. It's very similar. What was the condition for the just p hat? How do we figure out if that sampling distribution is approximately normal? Just p hat. So it was n times p and greater than or equal to 10. So now we have n1 times p1 greater than or equal to 10. n1 times 1 minus p1 greater than or equal to 10. You have n2 times p2 greater than or equal to 10. n2 times 1 minus p2 greater than or equal to 10. Alright, so same thing, we just have twos, or ones and twos, because we have two samples now. The other thing that needs to be true here is that the samples need to be independent of each other. So they should be independent of each other as well. We don't want one to be influencing the other one. We didn't talk about it for the proportion, but if they were in a scenario for a mean where one was influencing the other, you'd be in a matched pair scenario, not a two sample scenario. Everybody ready? We're just gonna do the same kind of thing we've been doing. We're gonna find the probability using those things right there. So we have a very large high school. The junior class has 550 students, 52% of whom have a part-time job. The senior class has 600 students, 46% of whom have a part-time job. The student council selects a simple random sample of 40 juniors and an independent simple random sample of 35 seniors. So again, if they're a junior, they're not a senior. Let p hat j minus p hat s be the difference junior minus senior in the sample proportions of students with part-time jobs. Again, instead of using ones and twos, they're just using j's and s's. Alright, this right here, the 550 is what? This is the population size. This is the population of the juniors. The 52% or 0.52 is what? The true proportion of juniors. And then the same thing here for the seniors. The 600 is the population size of the seniors. The 46% or the 0.46 is the proportion for the seniors, the true proportion. We take a simple random sample of 40 and another simple random sample of 35. Those are our two sample size. So when I find the shape of the sampling distribution here, so I would take the sample size, sorry, let's use J's since I use J's. So J times PJ, so I'd have 40 times 0.52, which is 20.8. We'd have 40 times 1 minus that. Again, the one number is 20.8. The other number has to be 19.2 because why? They have to add up to 40. Basically, you're reallocating that 40 based on what you think is true about the population. Same thing, I'm going to do the seniors. So I'd have N seniors times P seniors. The seniors, we took a sample of 35.46. That number ends up being 16.1. We do the other one. Again, they have to add up to 35. This one is 18.9. So we're approximately normal because all of them are greater than or equal to 10, okay? Go ahead and we'll just do one big interpretation at the end. And we'll talk about the verifying in a second. Right now, why don't you just calculate the mean of the difference and find the standard deviation of the difference. And I'll just put the formula sheet up here again so you can see those formulas. And then I'll talk about the other little things and we'll do the interpretation. Here's the formulas again. And check with your neighbors, see if they got the same answers as you. Alright, what do we get for the mean? 0.06. What do you get for the standard deviation?
114.
Yeah, I'd put 115. I don't know if it's just rounding. Alright, the interpretation, I'm just gonna do one big interpretation. The verify both types of independence. So when it says both types, like I said, the samples need to be independent of each other. And they are, it said in the beginning that we took a sample of juniors and an independent sample of seniors. Again, you just don't want them to be the same people. And the other check we would say is that 40 is less than 1/10 of the 600. No, the 550, sorry. And the 35 is less than 1/10 of 600. So both of those conditions have been met. Okay? Alright, to do the interpretation, I said in all possible samples of 40 juniors and 35 seniors, the mean of the difference of the sample proportions with a part-time job is 0.06, but that may vary by 0.115. Do you have a question?
I confused by the wording. It says that that may vary by 0.115. Is that like, I mean, that's stating the standard deviation. It was just like the phrasing of that sort of sounds like it's saying that it like varies
That may vary by 0.115, but the mean of the differences part-time, but the differences may vary.
So this typically varies by 0.115, is that right?
Yeah.
Okay.
Yeah, you could say typical. I was trying to put the two statements together as opposed to doing it one by one. Alright, so we're gonna do the same thing, but look at the differences in the means. Ready? I'm not gonna do an activity, but same idea. So you'd have a group of like juniors and you find the average height, you have a group of juniors, you find the average height, a group of seniors, you find the average height, you take the differences in the averages. So the mean and standard deviation of those are also on the formula sheet. I'll show you where they come from. These are the two formulas right here. Yes, just like before, that standard deviation formula is only going to work if both the sample sizes are less than 10% of their respective populations. It's approximately normal for the same reasons that it was yesterday, okay? So yesterday, if we were talking about the sample mean, so when we were just talking about the sampling distribution X bar, it was approximately normal if what was true? What? N was greater than or equal to 30, that was their central limit theorem, or, remember that was the call center data, or if it was like the kids, it's approximately normal if the population is normal. So if your population's normal, then your sampling distribution of the differences will be normal. If your population's not normal, then you're gonna have to check that central limit theorem. Okay? Alright, down here. Mu x bar 1 minus mu x bar 2. Again, thinking about the last chapter and this chapter. So the mean of the differences, it would just be, what's the mean of x bar equal to? Mu of x bar is equal to? Mu. So this would be mu 1 minus mu 2. Again, you've got an unbiased estimator. Because the mean of the mean of your estimates, the mean of your statistic is equal to what you're trying to estimate. Standard deviation, same thing as before. We have to add the variances. Same thing as before. You're going to have, I'll do it again without. So you'd have sigma 1, I'm trying to write it like how it's on the formula sheet, over n1, but you would square this, if you don't want to write it yet, because I'm going to get rid of the square, all this stuff. So what happens here when I square it is that the numerator is squared, right? So, but then the denominator, the square root's gone. Does that make sense what I did? And again, the same thing is true as what it was before. But again, the samples need to be independent of each other. If they were not, it would be a matched pair scenario. We don't want matched pair. Does that make sense? Go ahead and try the one on the back. When it asks you to do an interpretation, you can just do one big interpretation at the end. Remember, the order of subtraction is important. Check your answers with your neighbors. I tried to word it a little differently, Cora. See if this works better. I'm gonna put up the answer and then I'm gonna pass back the tests. I worded it a little differently below. If you're still writing, it's fine. Again, once I pass out these tests, make sure your phones are nowhere near your cups. You need to step out again. Everybody else in the room is taking the test, right? Yeah. Probably would have remembered if I didn't give you one. Any questions on that problem up there?
And the difference is, I think you might by someone that's from that.
No, it's just like The sample mean difference, and I don't know if this is in tons. The
Oh, in
difference in
tons.
I don't know if it's in
All right, I'm gonna take this away.